Hello everyone. Today, I'll present on enhancing morphological diversity and demonstrating control robustness of polyhedral modular rover. I'm Shingo Onizuka from the University of Kitakyushu in Japan. Thank you for being here. Modular robot systems combine small robot modules and can reconfigure them into larger robot structures. These systems offer three key benefits: versatility, fault tolerance, and lower cost. There is a large body of prior work on modular robots. Most existing systems rely on simple or highly symmetric shapes. They largely focus on control, docking mechanisms, and can reconfiguration strategies. The quantitative effect of module shapes on robustness has not been widely established. This study focuses on two ideas. First, we use polyhedral module shapes to increase assembly degrees of freedom and realize morphological diversity. Second, without adding sensors, we ask how much light control retuning can improve cross-terrain locomotion robustness, and we quantify it using power variability. Concretely, we run tests across terrain, payload, speed, and morphology factors, measure power, and use power variability as a dependent variable to estimate main effect, and map the effective regimes of shape design and control. The system consists of a body module, limb modules, and end effectors. The body houses the docking mechanisms and integrates power, computation, and sensors. Each limb has a roll pitch roll chain. The roll joints offer continuous rotation, and the pitch joints actuate up to 120 degrees. Docking interfaces at both ends let the limb attach to any body face, functioning as a leg or a wheel unit with its end effectors. For example, one body with four limbs and wheel-type end effectors forms a locomotion morphology. To realize morphological diversity, we impose several design constraints. First, single-limb traversal across body faces must be feasible without mechanical interference during face-to-face transitions. Second, the body should be highly symmetric, so we can build the same morphology regardless of orientation, preserving docking orientation freedom. Third, we balance internal volume and mass. As the number of docking face increases, overall mass growth must remain limited to keep payload capacity and operability. To satisfy these constraints, we adapt polyhedra, whose dihedral angle between adjacent faces are greater than or equal to 120 degrees, preventing collisions with the limb's 120 degrees pitch motion. There are three constraints. First, a single limb must traverse a face and transitions to adjacent faces. Second, high body symmetry, so identical morphologies work regardless of orientation. Third, sufficient internal volume while limiting mass growth as the docking faces increase. Under these constraints, we screened mainly Archimedean solids. The key parameter is the dihedral angle, face-to-face transition, use approximately 120 degree pitch, so dihedral greater than or equal to 120 degree is preferred. Shapes with a smaller angle or poor volume to mass trade-off were discarded. We therefore selected the Ryomovic octahedron, high symmetry, many planar faces, adequate internal volume, and suitable dihedrals, enabling multi-directional docking and reliable single-limb transitions. The body is built from face-to-face panels and vertex blocks. This architecture provides stiffness for transition loads while keeping the face panels as modular mounting points for compute power and sensors. To show morphological diversity, we evaluate a simple locomotion task. Two goals. First, define one common task for fair comparison. Second, fix the measurement and the metric. Using a Ryomovic octahedral body, we build representative 3- and 4-wheel morphologies. They come from combining body orientation with a selected limb docking faces. In this study, we assemble and test the 5 candidates highlighted in red. Task: straight line motion at constant speed, 15 seconds, and at 10 degrees per second. During motion, we record per rim current and voltage, compute instantaneous power, and obtain per rim power profiles. Metric takes the standard deviation of each per rim power time series, then average across the 3 to 4 rims. This is mean motor STD. A smaller mean motor STD means more even load sharing and thus greater robustness. So, the Ryomobi octahedral body supports 3 and 4 wheel forms that run straight at constant speed. We record power and quantify load distribution using mean motor STD. Results from the previously described experiment are presented here. At this stage, multiple representative 3 and 4 wheel morphologies on the polyhedral body achieved straight line locomotion at constant speed. Across the tested morphologies, locomotion was confirmed under specified conditions. Per rim current and voltage were recorded during motion to compute instantaneous power, per rim mean power, the overall mean, and variance are reported. The focus here is a load balancing trend by morphology. First, consider the plots of mean power, per rim, and the overall mean. 4-wheel morphology A shows the highest total mean power across rims, approximately 140 watts. Differences across rims are pronounced, indicating load concentration on particular rims. Morphology C similarly exhibits partial load bias, whereas 4-wheel morphology B appears comparatively well balanced. 3-wheel morphologies E and F tend to have lower overall mean and smaller inter-rim variability. Examining variance clarifies this trend. Morphology A shows a large variance, while 3-wheel morphology F shows small variance. Overall, the results indicate an advantage in energy distribution for the 3-wheel morphologies, reflected by lower power variance and more even load sharing. From the previous experiment, locomotion was confirmed across multiple morphologies and load sharing ranged from even to highly biased. Two issues emerged. First, startup variability and small initial posture offset produced transient power spikes, and uneven load distribution which could inflate variance depending on the morphology. Second, the test space was narrow. Terrain was mainly matte. Speed was fixed at 10 degrees per second. Under those limits, the effects of terrain and speed were not cleanly separable. An upgraded experiment was designed with a simple aim: suppress spikes and reduce load bias without adding sensors. 3-light software adjustments were applied: empirical retuning of rim PID gains, initial posture corrections, and synchronized start of all rims. No new hardware was introduced. The task and measurement remained the same: straight motion at constant speed, per rim power recorded. The evaluation metric remained mean motor STD. The condition space was expanded in 3 dimensions. Terrain included mud, floor, and sand. Speed included 5 and 10 degrees per second. Morphology focused on 2 4-wheel configuration, Form 1 and Form 2. One caution before looking at results. Because the condition set was expanded, the depth set became imbalanced and did not form a strict paired AB design. Interpretation therefore focuses on factor-wise effect in watts, rather than strong before and after visual comparisons. This section overviews the distribution of power variability in the upgraded experiment by morphology and terrain. First, by terrain, boxes indicate the interquartile range IQR, whiskers show the range, and dots denote outliers. On mud, medians remain stable and overall spread is limited. On floor, occasional outliers are observed. On sand, medians are comparable to other terrains, but the upper range extended notably. In summary, low-friction terrain tend to amplify variability and make outliers more likely. Next by morphology. Differences between forms are small. Medians and IQRs are similar, suggesting that under the upgraded setup, operating condition and environment dominate relative to morphology. Next, the distribution of power standard deviation is reviewed, followed by conclusion from an OLS main effects analysis to identify which factors like increases in variability under the upgraded conditions. A main effect OLS analysis is applied. The dependent variable is the mean motor STD, the mean of per limb power standard deviations. The model includes main effects only. Interactions are not included. Coefficient represent change from the reference level. Negative indicates reduced variability. Positive indicates increased variability. Bars shows point estimate. Black lines shows 95% CIs. Intervals crossing zero indicate non-significance. First, consider the distribution of the standard deviation for baseline and upgraded dataset. Although the upgraded set includes lower friction and higher speed conditions, the peak occurs near similar values, indicating little change in the central tendency. Now, to the OLS coefficient plots. For the experiment factor upgraded in the reference, a positive coefficient for baseline indicates larger variability than upgraded, i.e., the upgrade reduced variability. For speed 10 degree per second versus 5 degree per second reference shows a positive coefficient, indicating increased variability at higher speed. For terrain, sand will a positive coefficient relative to matte floor reference, indicating higher variability on sand. In summary, control upgraded act in the reducing directions, 10 degree per second, and sand act in the increasing directions. Morphology difference appears small. To close, the main points are summarized for clarity. This study set two goals. First, a rhombic octahedral body was used to expand assembly freedom and realize 3- and 4-wheel morphologies. Second, robustness was assessed through power variability to test whether light control retuning without extra sensors can help across terrains. In the baseline phase, multiple morphologies were assembled under limited conditions with flexible body orientations. In the upgraded phase, the metric mean motor STD, defined as a mean standard deviation of per limb power, was shown to vary strongly with operating conditions rather than showing a uniform decrease. Operating conditions shape the outcome strongly. Higher speed at 10 degree per second increased variability, and sand as a low friction terrain did the same. Morphology effects were present but smaller than the effect of speed and terrain. Future steps are planned. Automating the initial posture configuration will remove manual alignment. Interaction effects among factors will be evaluated. Longer distance and longer duration trials will be conducted. That concludes the presentation. Thank you for your attention.